Okay. Good evening, everyone. It's my pleasure to introduce our speaker today, Yonatan Bisk, who is an assistant professor in the Language Technologies Institute at CMU. Yonatan got his PhD degree from the University of Illinois at Urbana-Champaign and spent time at University of Southern California's ICI and University of Washington and Microsoft Research. His research focuses on grounded and embodied natural language understanding, and today he will be talking about their recent efforts on embodied AI. The stage is yours, Jonathan.
Thank you. Thank you for everyone for coming in the evening / my morning / whatever. Next time we'll do this in person. I was talking to a friend who just flew to Turkey, another professor here, and she was like, "Oh, next time we could do this all actually in person. It would be awesome." But yeah, so I'm going to talk today about. Well, I'm going to try to fit too much stuff in slides. As one does, I'll then run out of time probably, and we'll go from there. But I wanted to give a little bit of an overview of some of the stuff that I've been up to / the projects that I'm particularly interested in from the last couple of years. But I also wanted to give, and I think I'm probably preaching largely to the choir here, but I also wanted to give a little bit of a sense of kind of philosophically where I think this is situated in the sort of larger question of like where natural language processing is going, what's the relationship between it and embodied AI and things like this. And so the title for today is, Instructions, Abstraction, and Theory of Mind, because these are all things that have been on my brain for a little while here. So the larger context to start is, I like to position where NLP is coming from. And so this is this sort of opinion piece that I wrote last year with some friends. And the idea was that if we think about what NLP has accomplished, which has been phenomenal up until a few years ago, it was really based off of basically like the Wall Street Journal and a handful of other corpora. So we were really trying to figure out the semantics of words, the meaning of words from the context in which they appeared, where the context was very limited. And so we're depicting that here as sort of like, if you were trying to learn everything you could from a single book. And as we're all acutely aware, the last 3-5 years now, in part thanks to deep learning, has been this huge scaling. So all of a sudden we're like, well, wait a second, what if I just had all of the text of the internet? And so we have these large, massive language models that just continue to scale in terms of orders of magnitude and crazy amounts of data. So, I guess GPT-3 maybe was the temporary winner of this race, but someone else will show as something even sillier. And the nice thing about this is that there is a tremendous amount of knowledge on the internet in textual form, right? I mean, like Wikipedia has a tremendous amount of knowledge, more so than we were probably getting out of the Wall Street Journal. And then what we've seen recently, which is I think the most exciting to me, and I think a lot of the people here in the audience, is moving one step further and saying, well, wait a second, if we're going to be pulling information off the internet, we should try to sort of take the whole internet. So the whole internet also means the images of the internet, the videos of the internet. And this part, I think, while I'm not going to talk a ton about it in this talk, I think is sort of the most nascent. So I think that we're just barely scratching the surface right now in terms of the information that's accessible to us on the internet. And this particularly goes for the very limited amount that our community pays attention to, for instance, speech and audio generally, and then beyond that, sort of video as a whole, right? So we're seeing really, really great things where we're taking the transformers of kind of that we learned at large scale in World Scope 2, and we've broadened them into what we're calling World Scope 3. So we're like getting these multimodal transformers that have images and other kinds of access to that. But we're really just barely touching sort of what does it mean to do video. And I know that several people here have thought about sort of temporal cause and effect and all this other kind of reasoning. So there's like a lot of stuff that shows up once time becomes part of the dimension. And then also, I don't remember the exact number, but I was talking with someone recently about just the sheer amount of audio that's on the internet versus text. There's just like apparently like orders of magnitude more audio, which we're basically not touching. And so what we can think about is sort of these grounding dimensions. So if we're interested as language people, or I'm interested as a language person in this space, how am I viewing this space and how am I viewing language's relationship to everything I'm discussing? And so we could say like, well, let's start off with this kind of simple caricature of the space, focusing, let's say, language and vision. And so we have this kind of plane here, and we can put a bunch of maybe classic data sets onto this plane. And we could quantify, and here very loosely, what it means for them to be sort of more complex linguistically, or what it means for them to be more complex visually. And so I'm putting VQA, while it's classic, in sort of the bottom left corner. We have like really simple, clean images we're asking questions about. The questions tend to be about simple visual properties, which again is somewhat limited. And so that's kind of a really nice place to start. And then we have this question when we go along the other dimensions, right? And so maybe Epic Kitchens is a sort of better example of a more realistic domain. So we now have egocentric vision. So that's like what a person actually sees, what a robot would actually see. We have transcripts of people talking in a slightly more natural context. And so we want to move in those dimensions. And then a big focus of this talk, and I think, again, everyone who's interested in embodiment is actually saying, well, that's not the full picture. There's at least this other dimension here, which is action taking. And so we can start to plop down on this axis a few pieces of sort of historical or classic work. So what I've got here are this first one is a like sort of Chen and Mooney, AAI, I'm losing track of years right now, maybe 2012, maybe a little earlier than that, where you're actually looking at basically moving through a maze in a very sort of simple visual embodied space. This is from Visual Language Navigation, which I think most of us are familiar with, which was this sort of really big improvement recently in terms of taking natural language instructions and moving again through simulated homes. Now it's more real visually because these are real scans of homes. It's a little bit more complex linguistically because we're actually, these are crowdsourced annotations, but the action space is still very limited. We're sort of doing hops on a graph. And then this, popping on, this is Manuela Velosa's Cobots from a number of years back, also now something like a decade old, where you had actual robots that were roaming the halls trying to help people and answer questions. And here we've actually moved to real vision. So it's from an actual camera in the world, though it is indoors and limited in various ways. You have actual language because you have people interacting with this thing, though it could only handle a limited subset. And then you have actions in the sense of torques. So you have actual sort of motor control that's happening. And so the question for me is, if we move towards, for example, that sort of richer action space, that's sort of more realistic, how does that break all of our algorithms, and what does that change in terms of what we can actually learn in terms of language meaning? And so there's a couple of sort of obvious places that we would expect things to change. So one of those is this notion of sort of memory. So if we have larger action sequences, so in vision language navigation, you're sort of just hopping a few steps around a house. If you have these longer chain actions that you have to take, then all of a sudden memory, alignment, pre and post conditions, what has to come first versus second, and so forth, become really important. How do we learn that? How do we have models capture that appropriately? Also, I'm not really going to go into this in this talk, but there's this question of what the output space should look like, or what does it look like in the sort of most realistic setting. So maybe that's end effector position, maybe it's quaternions, maybe it's torques of motors. And the reason I'm bringing this up, even though this talk is not going to focus on real robots, though we have some work that tries to look at this, is that I want to make sure that when we're thinking about embodied AI, when we're thinking about embodied NLP, when we're thinking about where we're moving this field, that we're never lying to ourselves. We want to be really, really clear about what the actual goal is, and then where are the places that we're cheating. And we want to make sure that those cheats are things that actually will generalize in the future, so that we're not sort of just creating a toy task for the sake of toy tasks, of which I, as many of us are guilty of doing, particularly earlier in my career. And the last thing I'm going to touch on a little bit in this talk is where we're just starting to go, which is sort of this question of theory of mind more generally. So another complexity to language is not just linguistically in terms of, oh, well, I've got a larger vocabulary, I've got more nested compositional structure. The real theory of mind is language, right? So the real language is theory of mind, excuse me. So basically, like, I need to know what to say. And the way I determine that is by modeling what I believe your world is, your understanding is, and that determines my linguistic input and output. And so if I'm not doing that, I'm not really sort of doing full language. We're not going to do full language, but I just want to put it on that axis. So sort of like that's where we want to go. And again, we can ask these questions about how that's going to break any of our existing systems. Places where we've assumed that we can kind of treat all agents the same. So are we always interacting with one conversational partner versus lots of conversational partners who all have different prior knowledge, different context? And so how do we actually incorporate that into models in the long term so that we get to this sort of ideal place where we're actually sort of learning that kind of butler robot that is moving around the world, is following instructions, is understanding language, is understanding us, is adapting to us. You know, this really far off, grand, not in my lifetime kind of vision, but we want to make sure that at least the research directions are kind of pointed in that direction. The sort of the technology that we're producing are actually building blocks towards that. So the big questions then become, if as we make these realistic changes, how do these change or inform language? How do these shift us? And so I'm going to now come down from my sort of high horse up here philosophically, and to make this a little bit more concrete. And so we're going to talk about world scopes 4 and 5. So I said 3 was once we got to the entire multimodal internet. So world scope 4 being action taking. And so the simplest version of this being instruction following. In this case, in a simulated world. I'm going to talk a little bit about our Alfred benchmark, which some of you are maybe familiar with, and some of the advances that have happened recently. Moving from that, when you're giving instructions, if you're talking to a person, you are always, as we were just saying with Theory of Mind, you're always calibrating. And so you really ideally want to be working at a slightly more underspecified level. You don't really want to be spelling out in sort of robotic language, very low level details. So what does it look like to try to build systems that are a little bit higher in terms of their abstraction, but still executable? And then finally, as I was noting with Theory of Mind, World Scope 5 is saying that the ultimate sort of meaning is not just that you can see the world, that you can interact with the world, but that you're also starting to understand the hidden world that is inside everyone else's minds. And so this is where Theory of Mind starts to come in. I'm going to talk about some early work on sort of few-shot language coordination in this space. So to make this more concrete, as I was just saying, we want to have some sort of a simulated environment for the start where we can do some research that eventually gets us to our killer robots in the wild. And so this question is, how do we get to this place where we have, in this case, I'm using Herb, who does not understand language, but Herb, this is from a demo where Herb actually takes the cream out of an Oreo. So a very sophisticated mobile manipulator. How do we get to the place where we actually have a robot that we can talk to and can actually help us around the house? Maybe not so much with a knife. And so the couple of things that we wanted to accomplish with this initial work were, we wanted to look at where we felt there were limitations in the existing benchmarks. For example, I'm going to be comparing oftentimes to room with all the appropriate level of respect to Peter Anderson, who is a good friend, very good work, but that's going to be our basis for comparison. So longer horizon plans, state changes, language complexity, underspecified language. These are the kinds of things that are not present in simple navigation tasks, particularly in things like vision language navigation, as is defined by room to room, because they're hopping around sort of smaller houses. And you can make these large multi-meter leaps. There are things that we're not going to accomplish in this work. Again, being very honest, we're going to make some progress, I think, in the interaction space by moving away from simple toy characterizations of interaction to masks. So we're going to require that the agent actually predict a mask of what the object is in the world that they want to interact with, but we are still going to keep some discrete actions like pickup, which is obviously not realistic. There is no API call on a robot for pickup. But we felt that masks were an okay compromise on this trajectory because these are, it's one of those technologies that's actually necessary for grasping. So if you're going to run GraspNet or some other kind of thing like this, you are going to do modeling of masks and segmentation of the world. And so this is sort of a prerequisite technology on that road. Okay, so this work appeared at CVPR last year, and then I'll talk a little bit about how sort of the runaway progress that's happened over the last 12 months. But the basic idea is, as I've been sort of trying to sell you on this idea that we're going to have this butler robot that we can talk to. So what does that look like? So for us, what that looks like to start is that we've got a simulated houses. These are built inside of AI2 Thor, and you've got some sort of high level goal. In this case, put a gray bowl with a watch on it in it on the end table. So you have to find the gray bowl, you have to find the watch, you have to put it in the bowl, you have to put it on the end table. So you've got this sequence of actions that all have to be executed in order to achieve this high-level linguistic goal. You have to interact with a fair number of different objects and a fair different number of contexts. And so in particular, we're going to try to characterize 7 basic tasks that we think that an agent needs to be able to perform. So the most basic thing, if you're in an environment, you have to be able to pick something up and you have to be able to put it down. So pick and place. Because I said we were interested in things like memory, we were curious, well, what if we just take that really simple task and we sort of double it? So there's two of an object in the environment. To what extent do we end up with systems that are in, get themselves in loops, they get themselves sort of lost, they can't keep track of the fact that they've accomplished one piece versus another. Then we have this notion of containment. So if I'm going to stack two things, as we were just saying with the putting the watch inside of the bowl, so understanding that there's sort of an order of operations in order to accomplish some sort of final state. A really simple one is examining in the light. So finding some object, bringing it to a light source, looking at it sort of up close. So these are all things where we have longer horizon tasks. We have some amount of memory. We're going to have some issues. There's some pre and post conditions, but they're still more similar, I think, to the navigation task than the following three, which are heating, cooling, and finally rinsing. The difference is that when we move into this space, we have immutable state changes. So if I've cooked something, I can't uncook it. And so that means that a lot of the technologies that we've been seeing really blossom in the navigation space, which leverage things like search algorithms with backtracking and so forth, have to be used carefully. You can't explore things that you can't undo. And so it's not that we don't want to have those technologies, but we want to sort of force models to understand when it's appropriate to leverage those kinds of things and when it's not. So these are some of the examples. Another one, which is a component that you're seeing actually here in the cooling at the moment, that you're actually working with a slice of something. That's another one of these things. It's not a high level goal for us, but if you slice something, you can't unslice it. Okay, so we want to collect this data. So let's start off with the sort of most generic concept. So what's the most generic concept? Well, I want to stack, in this case, let's say a fork and a cup on a specific countertop in this kitchen. And so what we can do is we can just define that as a tuple. And then we can pass that, because this is inside of a simulator, we can sort of formalize that as logic, which we can pass to a planner. So we can, in this case, a PDDL planner. And so we can instantiate the worlds. We can say, like, here's an instance of that kitchen. We're going to put the objects in some random location. We're going to tell the planner it's going to have ground truth information about where everything is. So all it has to do is now execute the shortest path plan in order to accomplish this. We're going to take that video. We're going to show it to some humans. We're going to be like, hey, what is this? What are you seeing here? Give us a step-by-step breakdown, give us a high-level description of what was achieved, in other words, basically describing the tuple, and then also give us low-level instructions that describe each of the steps that were involved here. So that's the closer corollary to the existing literature. Now, because it's a simulator and we can just instantiate these objects willy-nilly, there's nothing that prevents us from doing this multiple times, which is exactly what we end up doing. So we say, like, we're going to take that same exact tuple, we're going to take those same exact objects, we're going to take the same exact room, but all the objects are now located in initial random configurations that are different. And so what that means is we have the same high-level goal that's going to be true for all three of these, even though the low-level execution may look almost nothing alike. We're still going to annotate each of them with language descriptions. So now what we have here are two different types of sort of linguistic diversity in some sense. So we have an overlap. We've got the notion that there's three different descriptions of low-level actions, which are going to describe the same thing differently. And then we're also going to have 9 high-level descriptions, which could apply in principle to any of the 3 instances. So we have this kind of many to one at a couple different places. So we've sampled these environments, we've executed these plans, we've annotated this language. So to give you an example of what this looks like, here's just one example from the paper. So I was saying we have a bunch of these different basic tasks. So if you zoom in on one, like clean and placing something, you get this high-level goal: put a clean sponge on a metal rack, place a clean sponge on the drying rack, put a rinsed out sponge on the drying rack. So all 3 of those, again, are describing the same thing. So they're all describing the same final condition for the world. And then we have this lower level language right below it. So you can see that this is, again, describing the same sequence of low-level actions, but slightly differently. So go to the left and face the faucet, turn around and walk over towards the bathtub on the left, walk forwards a bit and turn left to face the bathtub. So all of these are trying to describe the same thing. They do in principle. I'll show that in a second, but in different language. So you have this low-level instructions. If you want them, your goal is go about the world. So let's now revisit the promises from a second ago. So what did I say our goals were in terms of introducing this benchmark? I said longer horizon plans. Let's start there. So the comparison, the natural comparison at the time, though, I think there is an argument to be made based off of some work that's shown up on arXiv in the last few months that there's some, we should update this, is that when we were comparing ourselves to, for instance, touchdown, virtual home, or room to room, substantially longer trajectories. So the total number of actions required on average being, roughly 50 with some very long tails. By comparison, for room to room, again, not a trivial task, but that navigation task, I believe it averages like 7 steps. So a much shorter trajectory. The second one was sort of language complexity. Language complexity, as we noted a second ago, is actually complex to define. So I'm not going to be able to cover it here, but a simple metric being, let's just look at instruction length. And so what we're seeing is that on average, these instructions are just under 100 words, simple tokenization, which is on par with touchdown, touchdown being a navigation data set in New York City, moving around the actual streets. So getting really some nice real imagery and sort of real complexity in the world. But much longer than what we've seen in some of these other benchmarks. And then, as I was harping on a second ago, this notion of state changes and underspecified language. So if I say something like place a hot slice on a bread slice on the counter, I haven't told you how, I haven't told you any of those things, any of the sort of prerequisite steps. So if you're going to work directly from the goal, it's not that you can't do it, but it is going to be more difficult. And so you'll have something like this. You'll have a loaf of bread on the counter. You have to be holding the knife in order to execute a slice command, at which point it magically slices. So again, not quite realism, but that's one of those things that you can't undo. You could then take one of those slices, you could take it to the microwave, you could heat it up. And this is, again, something which you sort of can't undo. You've sort of fundamentally changed the texture and the nature of the bread after doing that. And then finally, the masks and the action space. So let's say we want to do something like wash the cup. So the simplest thing that you could imagine doing is implementing that as your API call. You could be like, oh, yeah. We're just going to have something called wash. The problem is that what you're, as I was saying earlier, every time we make a decision like that as language people or simulator people, what we're really doing is passing the buck to someone in robotics and making their lives even harder. And so then the question was, could we take a baby step closer? So what does it look like to wash the cup? Well, if you're holding the cup, then we are going to cheat a little bit. And we're going to say that put in is a primitive. But we aren't going to cheat in terms of where to put it. So we're going to require that the system actually produce a binary mask over the image that specifies the basin of the sink. And so the idea here is that we are, again, closing that gap just a tiny bit. You now have to have a system that actually understands what the heck a basin of a sink is. So you have to understand where the sink is, you have to understand where you can put things inside of it and so forth. And the same thing is going to be true for each of the next steps. So for example, now that we've put the cup inside, you can maybe see it here over on the left side inside of the sink. We're going to have a toggle action. That's a high level action. So that's a cheat. But you're going to have to specify what you're toggling. In this case, you're toggling the faucet itself. This turns out to be very difficult. So inside of AI2 Thor, one of the really nice features is this notion of seen and unseen houses and environments. And they've actually built custom assets for every single one of these. So that means that no two faucets look alike. And so that means that ideally, a system would sort of not have a problem here. So a human shows up, you see, you walk into some crazy rich person's house and they've got, I don't know, a gooseneck faucet that actually has wings and looks like a bird. You would still basically be able to figure out what's going on there because you have some functional understanding of what it is, where it's placed, its relationship to the sink basin and so forth. Our systems don't have that. And so what ends up happening is it's a reasonably small number of pixels that they need to figure out are sort of the thing that they need to interact with in order to, in this case, turn on the water, which then fills the sink. So that means that we've now sort of washed the cup for our purposes. And we would turn it off, pick it back up, and so forth, picking it up, requiring, again, a mask over the actual object. So the temptation here is to say, well, fine. It's complicated, it's longer, but we've got this magic, this deep learning thing. We're just going to take everything, we're going to shove it into this big model, and we're just going to run it and see what happens. And so we went ahead and did that for you. So take this long instruction, run it through some sort of, let's say, BiOSTM encoder, take our scene, run it through ResNet, get some pre-trained features out of it, take those two things. We have a recurrence because this is a an action taking task, and so we have to remember where we were, where we're going. We stick it into this recurrence, and then we predict some high level action in the mask that we actually need to take. Okay, so does this work? Well, so in order to define if something works, we need to find metrics. So the two metrics that we're going to focus on here are success rate and goal conditions. So success rate is exactly what it sounds like. Did you accomplish the task? Did you do everything you were supposed to? And the goal condition is basically saying, since this is an environment that's inside of a simulator, we actually have a little bit more control over sort of the evaluation paradigm. So we can actually check, for example, if I asked you to put a clean apple in the fridge, and you went and got the apple and you put it in the sink and you turned on the water, but then you never turned off the water and you never put it, so on and so forth, we could want to give you partial credit. So that's what goal condition is going to do. And as I said, we're going to do this on the seen and unseen splits. So I just updated this like last night just to double check there wasn't something new on the leaderboard. So I'm going to start off with our really simple kind of tabula rasa style deep learning approach. Not great. So really, really low success rates, both in seen and unseen environments, a tiny bit better for partial credit. What we've then seen is a bunch of really cool innovations. So Mocha took us one step further by basically trying to modularize the approach, trying to use some slightly better pre-training components. We've then seen a bunch of advances, including, for instance, the use of transformers. I want you to note, as we're going through this, the disparity between the gains on the seen environments and the unseen environments. So really starting to learn the environment, starting to learn the kinds of action spaces we want to take here. And so we've got a slew of these methods that are continuously climbing. You'll notice we are interested in the unseen generalization. So I'm sorting by that. So we have a sort of monotonic climb in terms of unseen, but much lower, about a half to a third of what we're seeing on the seen environments for both success rate and goal condition. So all of these are taking a bunch of different approaches, but the main things to sort of know is that they're throwing basically the kitchen sink at it. So we've got pre-trained BERT, we've got mask RCNNs, we've got pre-trained segmentation, we've got all kinds, like everything, supervised computer vision that we can, and large scale language at this task in order to try to get there, and we still have a long way to go. I'm paused before this final one because this final one is fundamentally different than the others. So as I said at the very beginning, one of our real goals is that we want to move to a place where we're interacting with these agents at a high level. We're interacting with them with the language that we would want to interact with one another. And that means abstract and underspecified. And so this final system, to my knowledge, is the only one that actually does not use any of the low-level instructions I was giving you, showing you before. They're only working with that high-level one, and then they're performing sort of exploration and trying to execute the task directly from that. They're still doing some very sophisticated stuff. This is Valts Blukas's work out of U of Artsy's lab, and they're doing this really awesome work where they're doing, very good depth estimation for 3D map building of voxels and so forth. And so we're seeing some nice progress here. Okay, we have a ways to go though. So if you actually just ask a human to do this, it's not that hard. So these are not complicated tasks. You get kind of this sort of blinders on when you're staring at these systems. You're like, oh, look how hard this is. It is hard, but it's actually quite easy for people. So then this begs a kind of a natural question, which is like, why is it so hard? And very much want to understand that question because I want people to beat this. I want people to destroy this benchmark because I want to see the technology that's produced in the process, and then I want to be able to produce something that's even more realistic that takes us a step further. And so there's like a few hypotheses you might formulate. You're like, oh, well, maybe it's the fact that there's so many different ways to refer to things in the scene. And that's why people are throwing these pre-trained models at it as much as possible. Maybe it's this long horizon state tracking thing. And so maybe the transformer is not really good at that. Maybe the LSTM is losing memory. Maybe it's the fact that you really want to have sort of implicit scripts. Maybe it's the fact that each of these things are hard, and when you try to learn them all jointly, it's even harder. So you don't have a clean training signal. So I want to focus conceptually on this one piece for a second. So if I have something like place a heated apple slice on the large table, I haven't told you anything about the environment. I haven't told you what kitchen you're going to be in. You already know what you're going to do. You already have taken this and you said, well, apple slice may not exist, in which case I'll need to create an apple slice. And you're like, oh, it's heated. That means that after I have the apple slice, I'm going to have to, find something that can heat this up. The large table, okay, I'm going to have to isolate where that is. I'm going to have to place it there. You've already building out this script, and you're building out recursively because you know that creating a slice actually might mean that you need to find a knife and then locate the apple and slice it. So the fact that you can do this kind of script planning in your head in the complete abstract is something that's missing from our systems. And that gets even more concrete when we just add a tiny bit of extra information. So if I plop you into the kitchen and I say, okay, spin around and just look around, but you can't move, and which is what you're seeing here, you could now take each of these things and make it even more concrete. Right? So now you're maybe noticing, oh, it looks like there might be some apples here on the table. I'm only noticing one table, so maybe that's the large table. I'm also noticing what looks to be like a handle and something silver. That might be the knife that I'm going to need. And so if I was to ask you at this point to write down a set of low-level instructions, you could basically execute it okay with your eyes closed. And so this ability of ours to take something high level, create abstract plans out of it, instantiate them, execute them, is something that we don't have in our systems, obviously. And so when we're training at various sort of end-to-end tasks, one can ask about what is happening implicitly in the middle. And so in an attempt to kind of understand that problem a little bit better, this is not necessarily a new benchmark, but this is that what we then did is we said, like, let's try to factorize that problem and try to sort of stare at it a little bit harder. So if we have something like, this is from, sorry, skipped over that quickly. This is iClear this year. So if we have something like that high level instruction, and then we have some environment that we plop you in, and then we say like, oh, you get a reward if you did it correctly or not, you could try to train this with some sort of like RL end-to-end thing. We were not successful at doing this. You might be much smarter than us. And if you're able to get it working, I would love to hear about it. But what we decided to do was say, well, let's try something really cheap. Let's just assume that BERT is good enough, which is what you were seeing in some of the more recent things for Alfred as well. So let's just go ahead and say, like, that gives us our lexical representations. They're probably basically perfect. Let's go ahead and assume that ResNet is doing the same thing for us on the vision side. These are, offline trained, large amounts of data and so forth. So then we have this question, which is we got to have this thing that does this planning in the middle. We got this brain. Let's come back to that in a second. But we need to feed those signals in, which we're going to assume for the moment are basically perfect. And then let's try to make the output as easy as possible as well. So we're going to assume that Mask RCNN does a really good job of segmentation, of selecting objects in the environment. And so if we've done that, then the only problem that we have is the brain. The only issue we have is not the interacting with the world, not finding the objects, but just learning this sort of script, this planning component. So then the question becomes, can you train that on its own? Can it learn to explore on its own? So one way to do that is to simplify, the rest of the world. So in text world, which is what we choose to use here, you get this kind of really simple description of the environment. You're in the middle of the room, looking around you, you see a dining table, a stove, a microwave, a cabinet, and your task is to put a pan on the dining table. So what do? Again, this is very similar to what we were just doing a second ago. You've already built up a set of sort of possible next actions that you think are reasonable, like going to the cabinet, because you're looking for the pan, it might be in the cabinet. You get to the cabinet, it turns out it's closed. What are you going to do? You open the cabinet, turns out that the cabinet was empty. So what do? You replan. This time you go to the stove. That's another logical place to find a pan. In this case, you end up being successful. You find it, you complete the task. So here what we've done is we've basically taken a long horizon task, shrunk it really down to like a handful of actions, but actions that still involve things like searching, involve failure, involve understanding of the basic dynamics of the environment. And for each of these things, we also have an implementation in Alfred. So we have a mapping to moving ahead, to picking up either with Oracle actions, because we have access to the simulator's primitives, or via a learned model. So here we have rotate left, we have pudding, and so forth. And so we have text world on the left here, we have AI to Thor on the right, and we have this mapping, at least for most, not for all of these actions between the two, so that we have this kind of ability to maybe explore over here and then test over here. So then this is what you end up factorizing the problem as. You're basically saying, like, well, we have three pieces. We have a brain, which knows what it gets some set of observations. It knows what the goal is, and it needs to produce some action. We have the vision system or state estimation. So we've got the scene in front of us, and we have to figure out what the objects are. And then we have the body controller, which is taking in the visual state, is taking in the action that's supposed to be performed, and then it's actually executing it in the environment. And so then the idea is that we can try to train this text world system. We can try to train that brain over on the left, and we can use sort of fixed or pre-trained components for the other two. Okay, so how well does any of this work? So here's a subset of tasks from the environment you'll remember from before. If we simply train a system, this is in text world, testing it on a new text world environment, so not embodied yet. Then if I simply take an existing model that works in the text world environment and I apply it here, then what I tend to find is, there's some tasks it's doing okay at, but not amazingly. So the important thing to note here, well, here, let me just show you a couple more results and then I'll come back to this. So if we allow this system to do exploration, in general, we see a huge improvement. And if we also let the model do sort of a better job, we incorporate sort of better beam decoding and reweighting of trajectories, it's even better. So this is not perfect. And so that's sort of an important note, which is that even in this environment, even in this sort of simplified case where I basically said, don't worry about the physical world. All you have to do is know where objects tend to be located. You have to remember to come back to things and so forth. The task is still not solved. So that indicates to me, at least, to us at least, that part of what is hard here is this script learning, is this planning component. It's not simply an issue of, oh, well, if we could solve computer vision, we would solve this embodied task. These are not the same, they're not synonymous. There's multiple challenges here. The other thing that we did is we then said, okay, well, let's take something that was trained in a text world, and then let's go ahead and run it in the embodied world. So we have this, this transfer, right? And so if we take that system, and as before we were just, if we train just on the expert demonstrations, it's reasonably weak. If we take the sort of full system that I was just describing on the previous slide, it's with the beam decoding and everything, it's a little bit better, but it's not great. And so again, we can ask this question from before, which is, all right, well, is that because we're using learned computer vision? In part, yes. So if we use oracle state estimation, so if we have ground truth masks, ground truth segmentation of objects, then we have this improvement of that system. But I've been showing you up until now as cheating. I've been using simplified language templates. If we instead work with real natural language, things get worse again. So there's a couple of quick lessons here. So two things to focus on. One, world models, state estimation, navigation, super important. And those are places that we need to be learning from the literatures have to be converging, right? So I need computer vision progress in order to make progress. But then also, unsurprising, and as a language person, you know that I'm going to say this, like the linguistic diversity is also hitting us. So I want to show one last slide here very quickly, which is on this topic, which is it sort of worth it? So if we focus in on just the pick and place for a second, and this is kind of in an oracle context, and we compare a system that has oracle segmentation and all this kind of stuff, so we're removing that for the moment, and we train a system that's purely in the embodied world to do pick and place versus one that's in text world versus one that's sort of a hybrid. What we find is that the one that was trained in text world actually generalizes better. And I don't think this is terribly surprising, but I do think it's still sort of a nice result to have. So the idea here is that if I'm training a system to perform even a really basic task, and I'm trying to do it in this kind of big end-to-end way, there's so many different features that it could be learning to sort of overfit to. And so, excuse me. And so if I remove all of those and I say like, no, all you're trying to do is understand sort of like the real basic dynamics of the environment, then the system is able to generalize better to a new environment because none of those features mattered in the first place. So I wasn't trained with those in the first place. I only knew about a subset of objects. I only knew that I could, how to interact with those things. And then I see those things again. I didn't know the color. I didn't know the height. I didn't know all these other kinds of things. There's all these other things in the visual space that the models are latching onto that actually make it hard for them to generalize, that we end up simplifying here. And then also it's the case that obviously training and simulation is much faster. Okay, so where does this put us? So let me rewind to where we were earlier in the talk. in some sense, I've made things worse. So I've now said like, okay, in text world, we can do goal, progress, maybe we can learn procedures and memory and so forth, but we need the real simulator. We need Thor in this case, or something, you know, akin to it if we want physics. So one of the things that text world can't do is it doesn't know if something can't fit in something else. It doesn't know that there's like a limit to how much stuff you can shove in a microwave. It doesn't, as I said, there was none of this visual information. So if someone says apple and they mean tomato or vice versa, that may be obvious to a vision system. It will not be obvious in text world because that kind of information just doesn't exist. And then obviously it's a realism of interactions and masks. And there's a whole bunch of stuff that we're not even talking about, which is if we move to the real robot, we have sensor noise, we have manipulation, we have motors. And so now that I'm going to totally run out of time, I'm going to very quickly try to run through one last thing. So this is hopefully not even remotely a solution, but at least gives you a sense for sort of where my brain is in terms of like trying to understand the questions that are relevant and necessary if we're trying to move that sort of world scope 4 agent forward. So there's all these kinds of generic questions of sort of processing of memory and so forth, and then how do we move towards increasingly realistic environments. The other dimension I said that we needed to tackle was this question of theory of mind. And so in this context, what we're going to do is we're going to start off with a very simple paradigm. So I've got, typically in a language learning context, I've got one person who speaks a language, perhaps fluently, and I have let's say a child that doesn't. And so a really simple way that you can approach this is you can use basically what's called referential game. So you say like, well, a lot of language learning is distinguishing between like objects. So we've got this description, which my student chose, which is a little bit gruesome. So look at the baby elephant standing next to its mother and so forth. And so so when it looks, if we have this child that's learning language and it sees these 5 images, it's trying to figure out, okay, well, which one of these am I actually supposed to be paying attention to? And then it has some, therefore, distribution over those. And then the speaker, the parent in this case, basically can correct them if they get it wrong, or can indicate which one, and they can update their models. And so the idea is that you're learning to sort of differentiate attributes. So the simplest way that you can explore this kind of question is that, well, we could say, well, instead of having a system that doesn't, a learner that doesn't have any language, what if we're just focusing on building better teachers for the moment? So let's assume that we have a teacher who is multilingual, but we have a child that's monolingual. So you could have this situation where the policy now, the model that has to be learned by the speaker is, how do I figure out quickly what language my listener speaks so I can adapt to them? So this is kind of, you know, a simple proxy for the standard environment. You know, you have a teacher in front of a classroom, you have a bunch of students, they all actually do know different things, and your job is to figure out how to tailor your instruction as quickly as possible to each of them individually. And so in this case, in this kind of toy characterization, what we do is we train a bunch of different models with different amounts of fluency in different languages. And then the teacher has to basically figure out, oh, the student seems to be doing best when I use, in this case, Spanish, in order to differentiate. And so we're going to take this concept, we apply it to the simple multilingual game, and then we're also going to apply it to sort of an ALF world setting. So to tie this back to where we were a second ago, same basic paradigm. But now let's assume that instead of having a bunch of listeners that are multilingual, that sort of know different languages, let's assume that they all have different amounts of experience in the physical world. So I know how to perform some tasks, that person knows how to perform other tasks, so on and so forth. Some people I can give high-level instructions to and they can execute it perfectly. Other people only understand if I do things, if I give them really low-level instructions. So this is, again, this kind of very sort of simple proxy for, I think, a pretty realistic setting where you've got like sort of, let's say, new trainees coming into a business, and each of them has some amount of different prior knowledge, and you're trying to sort of adapt to them. And so in the ALF world setting, what that looks like is you get something like pick up and cool the wine bottle and place it on the dining table. So you have this high-level description, and the teacher, you know, conveys this to the student. And then the student starts doing things. And what we're seeing on the right is then we have this sort of model of what the actual listener is thinking. So what we want to do here is we want to convey the goal and then try to guess as to whether or not we think that they're going to be able to do it correctly, if they understand where we're going with this. So if they go to the cabinet, you know what? That's a totally reasonable thing for them to do. They do need to eventually go to the fridge, so I'm predicting that that's what's going to happen. But they're opening the cabinet, still totally reasonable. They now have, there's a bottle of wine in the cabinet, so they've actually been successful. They pick up the bottle of wine. We're still reasonably happy, and our prediction is that if they understood the instruction, then they're going to do next is they're going to go to the fridge. That's the only way that they're going to be able to complete this cooling task. And then they go to the microwave. And so what that means is we've recognized a mismatch between the hidden latent world model of the student in this case and our model of them, the teacher. And so now what we need to do is we need to correct that. So we need to provide like a low-level command for correction. We have to say like, no, sorry, you've made a mistake. You actually need to walk to the fridge. And so the idea here is that what we have is language instruction or task teaching from this instructor. We have also, the instructor has a mental model of the student. So it has some prediction over the actions that the student should be taking. And then we want that teacher to be adapting as quickly as possible to the student. So seeing what kinds of mistakes they make and then changing their policy for instruction giving based off of that. And so in practice, what we do is we basically say, like, if you have some high level task like this, which has these sort of components, we're going to train the systems with different levels of abilities. And so the details don't super matter here, but the super short version of it is that you basically define kind of like a distribution over the different skills that are in this environment, over the different levels of abstraction, sort of concrete actions versus high level ones. And then we train a population of agents, each with different samples from this distribution. So each with different distributions of abilities, so that every time that the teacher interacts with someone new, they have a completely different setup they have to adapt to. And then what we can do is we can basically compare this listener that's doing this teacher that's doing this explicit modeling of the listener against something sort of like a naive baseline that just sort of is producing sort of the background distribution of instructions. And we can penalize them at different, because we have this new parameter, basically says like, how much do we care about sort of the efficiency of the language versus the performance of the student. So this is this kind of parameter that we really want to be trading off. And so we actually have sort of this mammal speaker for this, but the punchline is very quickly that what we want to be is up here. We want to be somewhere where you could psychically, which is impossible, but you could psychically know what this person knows and then give them the optimal set of instructions sort of for their abilities so they can perform a task as quickly as possible. In practice, where we are right now is we have a system which, by basically training over a population and training with mammal, is like a little bit better at adapting quickly when it starts to see some of these instructions, some of these actions failing, and we want to move that speaker up into the top left corner. We wanted to get it so it's even faster and faster. In the multilingual setting, to make this a little more concrete, in the multilingual setting, you see some of this emerge very quickly because, for example, if the speaker uses a word that's in a Romance language and it happens to be a cognate across a few different languages, then they're able to narrow down the search space very quickly. So they're learning sort of a search strategy for how to sort of optimize for their student. It's a little bit more complicated in this sort of action taking space, but it's a similar sort of goal. And so, I'll just close with a couple of quick, two final slides here. So one is just to give you a sense of kind of the questions that follow from here that are sort of on my brain. So we have this kind of question of like, well, wait a second, we've been talking about instruction giving, we've been talking about speakers, sort of what is the optimal teacher situation. That may not be the ideal situation, right? In many cases, we actually have collaboration. So how does any of this change if we have collaboration? What external knowledge should these agents have? So I was talking about pre-trained models, but maybe there's more information that you show up to any given scene with, which is not present here. And then, as I've been sort of harping on, is what breaks when we move to richer environments, to more realistic action space. And then finally, what is the role of sort of audio and gesture in this language learning space? So one of the things that's really missing, that we're only faking a little bit in the referential game, is in the referential game, if we have two images and the student gets it wrong, you could say that we're pointing by indicating which of the two or which of the N they should be looking at. But really in language learning contexts, children are looking at, for instance, the eye gaze of their caregivers, and that helps them narrow things down, helps them sort of understand the scene a lot better. So there's a bunch of these other kinds of signals which we don't even have access to right here. But to close, let me just give you the papers here. So what we were talking about mostly was this first one, some of the work that's followed from on top of Alfred, this abstract planning work that was at iClear, and then finally this work by Howe on Theory of Mind, which is at ICML. And so with that, I will close, and I can't remember if I was supposed to be 45 minutes or an hour, but I cut it right in the middle.
Thank you, Jonathan. Okay, we are open to questions from our audience. So to open for, maybe I can ask a question. So I'm not that much up to date on the state of the art on this visual navigation works, but for me, I believe that the memory is a very important component in these approaches, especially for these long horizon tasks. So for visual question answering, for example, there are some work which first tries to generate a scene graph and then additionally use that information for giving the correct answer. In these visual navigation works in Alfred, are there some works that tries to build the map of the environment, and maybe also this can be cast in a different way? Maybe you can also generate knowledge ways as you are exploring the environment about the objects you have.
Yeah, so totally great question, and there's sort of like a couple of partial answers here. So there's maybe two main things that I'll touch on. So one is that in Alfred, there are people that are building. So for example, that most recent work, they're building, they're using some combination of segmentation and depth estimation from single images in order to sort of build a voxel grid of the world that they can then use for planning. And so they are sort of doing that kind of initial step. It turns out that even though this is a simplified world, it's still the case that depth estimation can be, is difficult and stuff like this. And in particular, one of the things that's hard is that we actually limit the number of failures. So you're not allowed to fail more than 10 times. And what I mean by fail is we didn't want to have systems where this is in a given trajectory. So what a failure here means is like, we don't want to have systems that basically just sit there on a for loop running into the wall over and over again. So if you ram yourself into the wall 10 times, episode ends basically, right? So the reason this is relevant to the depth estimation and stuff like this is that this is one of these things that comes up, is that if you have not accurately figured out like the edges of tables, you know how if you open a cabinet, whether or not it's going to smack you in the head or not, things like this, then you can start to get into this place where you're actually hitting that limit pretty quickly, right? Because you sort of haven't sort of done that a good enough model of the world. So that's one of the places that, so I know several people are working on actively is actually like, to what extent is that a problem that should be solved via better vision techniques, or is that a problem that should be solved because of sort of like a better policy in the first place? So like maybe your policy sort of should do a better job of kind of modeling safe spaces and movable areas, things like this. The other thing that's not directly in Alfred, but I think is relevant to this discussion, is that there is a line of work so for instance, Sonia Chernova at Georgia Tech, and there's been some work that's followed up on it on sort of what they call in their paper, I think they call it robot common sense. But it's basically this question of like, well, what can I learn about attributes of the world via simply interacting with it? And so they're like, it's a it's a toy world, it's, simplified and so forth, but basically like, okay, certain things are made of wood, certain things are made of metal, certain things are up high, certain things are down low, certain things are, are huge, certain things are small. To what extent can we build all those kinds of, that kind of knowledge priors in advance? And so you could take the training scenes, for example, you could drop an agent in and it could sort of build this kind of basic understanding of the dynamics of the world. And then you could ideally use that as sort of priors for reweighting or as part of your agent moving forward. I don't know of anyone who's done that second piece. I know there's a fair bit of work in just learning those priors in the first place. But I really, really like this idea. I really like this direction because I think that it's very honest about the fact that we are working in built environments. So there's like a longer rant that I have here but basically, like, I think one of the things that tends to happen at the intersection of sort of language, vision, robotics, and stuff like this is that we talk about things in very general terms, but we are almost never giving language instructions to a Mars rover. So this notion that you want to be able to handle that is sort of maybe not as appropriate as understanding that the vast majority of the time that you're giving instructions to a system, you're giving it in a built environment, which was built by humans for humans, and therefore has basic structural priors for humans. The example I like to give is doors. This is maybe a longer answer than you were hoping for, but basically, like, if you're trying to figure out like how to interact with a door that you've never interacted with before, you're probably not going to push the top corners because it would be awkward for a human body to do that. And so there's like a pretty, small range of areas which make sense. And we're not in general, not in Alfred and not beyond that, I think, sort of taking enough of that sort of as inspiration in terms of constraining our searches, in terms of our models. So I think that your point is incredibly well taken. And I think it's sort of a general problem that we sort of have to do. And it's a little bit harder than seam graphs because of the fact that it's all depth. And then also the fact that if you've interacted with the world, you've changed it. So you need to be sort of updating it. Like the cabinets are now open, there's objects that are visible versus weren't visible, things like this. But conceptually, it's exactly that. It's just sort of a generalization of it. Yeah.
Thanks.
You have a question?
Yeah.
You go ahead, Ali.
Yeah, I was interested in the example that you showed, like an embodied training and a text-only or text-forward training example. And you mentioned that the text-only training or basically text-forward showed better generalization in terms of performance. Are these both like tested in the same environment, or how are they tested exactly?
Yeah. Right. Sorry. Thank you. Good point. They're both tested in the embodied world. So if you basically have access to an API, like for instance, I'm using API very broadly here. So a segmentation, pre-trained segmentation model or something like this. And then the question is basically a system which was trained with access to that segmentation model with features from that segmentation model versus one that is, in this case, let's say just using the names that were extracted from it. The one that doesn't have access to those extra features does seem, in our experience, to be generalizing a little bit better than the one that did have access to those features. But then the action space is the same. So you're still going to be choosing from the list of detections and segmentations and stuff like this. Yeah.
So would be the reason for this is that the environment is simulated.
So that's part. Sorry, is your question why is it generalizing better?
Yeah.
So my theory here is that it's actually because you're removing spurious ambiguities. So when you're trying to train this model and you have some instruction which is like, here's a dumb example. Pick up the apple. And let's say that in your training examples, apples are always red. And in the test environment, the apple is green. And I have the system which has this feature vector which comes in, which includes that. And if the model inappropriately determined that the action, apple sort of only fires if you have both the word apple, the detection apple, let's say, and the feature vector that contains the color red, then it maybe overfits really quickly in the training environment, but then it basically can't generalize. You remove that variable when you work in the text world. So the text world is not the answer. Sorry, I'm not trying to propose that we move to that space, but it was a way to explore this question of sort of like what makes this learning hard. And I think part of what makes learning hard is these ambiguities in terms, or these extra features that can lead to correlations that are not necessarily appropriate. So how do you figure out which things to actually focus on?
I see. So do you think that if we replace the simulations by real world examples, so the apples in this case wouldn't be only red or green, but we would have like a lot of different, we have a variety of things, and would that be good or not?
Yeah, so if I can rephrase your question, the way I'm interpreting it is you're saying, like, if we had good domain randomization, would that resolve this issue? And I suspect that the answer to that is yes. Whether or not we will ever have good enough domain randomization, sort of good enough diversity in order to do this, I'm not sure. And so there's a question there that I have no idea what the answer, but I love the question, which is how do you learn concepts, right? And so I think that's basically what this is. I'm saying, like, if you work in concept space, then you can generalize to seeing the same concept again. If you work in the real world, you get tripped up. How are we supposed to learn concepts in the first place? And I think your suggestion is a good first step, but I don't know what the full answer is. Yeah.
Thanks.
Yeah.
Thanks, John. Do you have any questions?
I think I'm good. I mean, we're going to meet up later, so we can ask him.
Where later is, I think, now.
Okay. Maybe we can have one last question, if there are any from our audience. Okay, if not, we thank our speaker, Yonatan. Yeah, these are really cool works, Yonatan. Thanks.
Thanks for hanging out with me instead of eating dinner or preparing dinner, as the case may be.
Thanks, Yonatan. We'll see you in a bit. So.